Hello, hello everyone. Welcome to the free GRE Prep Hour. Give me a little hello in the chat window if you can hear me. Hello, hello everyone. So you'll be able to see me on video, but because there are going to be so many of us in here, you guys won't be able to get up on video tonight. So these free GRE prep hours are something that we offer every couple of weeks to give you an opportunity to see a little bit of what the test is like, get some pointers, get some new perspectives for looking at the test. So we'll be looking at some of the most common issues that people have on the test, and we'll be thinking about how to approach the test in a thoughtful way. One thing that I'll be asking you guys to do is to pull in when we work on problems or when I ask you certain questions. An easy way to get everyone's responses all at once is to use the polling function. So you'll notice in the participants window, it'll be right above my name. There are a bunch of buttons. One looks like a smiley face, one has a person with a clock on it, one has a hand, and one has a little lowercase a button. So I want all of you to pull in, and here's what I want you to tell me. I want you to pull in, let's do it this way. Give me an A if you've taken the real test. Give me a B if you've taken a practice test, but not the real one. Give me a C if you've just done a little bit of studying, but no practice tests. Give me a D if you're totally new to the whole GRE experience. And don't tell me in the chat window, use that polling button, the little button that looks like an A in the participants window, right above my name. So we've got quite a wide mix in here. A number of you have taken the real test, but we also have a lot of people, most common thing, have done the practice test but not the real thing. And we have a couple total newbies in here, everything in between. So with these free GRE prep hours, what we're going to be doing is we're going to be taking problems, whoops, that just jumped ahead weirdly. We're going to be taking problems from the Manhattan Prep 5-pound guide. This is a big, giant book of practice problems, and it's a place where really you can practice more than you'll ever need, tons and tons of problems on every topic tested on the GRE. So just a note that the problems that we see in here, problems like it, you will be able to try on your own in that 5-pound guide or in any of the Manhattan Prep practice books. So here's what we're getting into tonight. One problem that I think people struggle with but is actually an opportunity to boost your score pretty quickly is if you get really good at quantitative comparisons. And we're going to talk about some GRE timing. In fact, I think I want us to do this. I want us to talk about timing first so that you know why it's actually important to nail quantitative comparisons. So for those of you who've taken the real test or who've taken a practice test, you'll notice that on each GRE section, it's pretty predictable how many questions you're going to get, the order that it goes in. On the quant side, you always get 35 minutes to do 20 questions. On the verbal, it's always 30 minutes to do 20 questions. One thing that hopefully you know is that the GRE is adaptive by section. So within a section, you can move around. Once you finish that section, it determines the difficulty level of the next section. So on GRE Quant, you're always going to get quantitative comparisons first. So when you're thinking about your time marker, when that 35 minutes starts, it'll be a countdown clock from 35 minutes. You'll work on QC questions, so you'll get 7 of those. And when it flips over at problem 8, okay, sometimes it's 6 questions, sometimes it's 8. Usually it's 7. So when the question type flips from quantitative comparisons to discrete quant, that's when you look up at the clock and you should see a 25 minutes remaining. Then you'll get multiple choice questions, discrete quant in other words. You'll get 5 of those. And then the question type will flip over to data interpretation. That's where you get charts and graphs. So when you notice that question flip, it's usually around problem 13, then look up at the clock and you should see 15 minutes remaining. You'll finish data interpretation. It'll flip back over to discrete quant, standard multiple choice, at problem number 16 out of 20, and you should see 10 minutes remaining roughly for those last 5 questions. So I recommend taking a screenshot of this right here so you can use this as a reference point. Instead of looking up at the clock at random and trying to guess whether you're ahead or behind, what you want to do is know where you stand. At any given point, are you ahead, are you behind, and know exactly when you're supposed to look at the clock. So quantitative comparisons. So there will be typically 3 data interpretation. So it usually, the order typically goes, you get 7 QC, then roughly 5 discrete quant, most of which are standard multiple choice. You'll get maybe 1 numeric entry and maybe a few multiple choice. You'll get 3 data interpretation, so the charts and the graphs, and then you'll get another 5 discrete quant. These numbers can change a little bit. Sometimes it's 1 more of these or 1 fewer of these, but this is roughly how many you'll get, and they will always be in this order. So the reason that this is important, when we think about those first 7 QC questions, if people spend too long on those, if you're spending 2 minutes per problem there, that's 14 out of your 35 minutes, and that doesn't give you much time for these other ones. What you want to aim for, if you're approaching these well, you should be able to shave quantitative comparisons down to about 1:15 on average. Obviously, there'll be some that take you longer, some that you can go through faster, but definitely way less time on these than on the discrete quant, some of which are long word problems, or data interpretation where you need to spend time on those charts and graphs. So what we're really going to look at today is a couple of techniques for how we can shave time off of our QC, look at some common QC structures, and think about how we can use that to our advantage in the beginning to have time to spare on the other things. So, for those of you who've never seen quantitative comparisons before, here is how those will work. You'll get some information up front, up on top, usually. Sometimes not. Sometimes it might just be blank. And then you'll always have quantity A and quantity B, and it's your job to compare the 2 quantities to decide which one is greater. The answer choices will always look like this in this order. So take a moment, give this one a try, and pull in an answer when you have one using that A button. This one seems really simple and straightforward, right? But let's actually take a look, because there might be something more complicated than we think. The GRE might be trying to trick us here. What they want us to think is, oh, x is 2 times y, so if it's twice as big as y, then clearly x must be greater, right? The thing that's twice as big is bigger. That seems reasonable, right? That's how we would think in real life, right? But they're messing with us here. If we pick A and assume x is twice as big, therefore it's greater, what are we forgetting about? What are we missing? Zero or negative numbers, exactly. So here is a mnemonic that I want you guys to keep in mind. The mnemonic is ZONEF. If you're thinking about what number should I think of, how do I make sure that I haven't forgotten something important, try testing 0, 1, 001, 0, 1, and then what do you think N stands for? Negatives. And then how about E? Well, I guess what would that mean in terms of testing? I like that idea of exponents. That's actually a really good guess. What it really stands for, or at least in terms of my mnemonic that I use, it stands for extremes. You want to test what happens with really big numbers or really small numbers. Those might behave differently. And thinking in terms of things that might sometimes behave differently, what might F stand for? Fractions. So when you're thinking about testing numbers, this should be the mental checklist that you use. So if on this one, x equals 2y, well, what about the case where y equals 0, and then 2 times that, x equals 0? Clearly, in that case, quantity A and quantity B would be the same. So if we test a case where quantity A and quantity B are both the same, which answer choices can we get rid of? A and B. Because remember, going back to here, with our answer choices, if this one says A is greater, what's implied here is that quantity A is always greater in every case. This would imply B always greater in every case. This would imply always equal in every case. So if you ever find a case where they're equal, it can't be A or B. If you ever find a case where A is greater, it can't be B or C. You get the idea. But your goal is always to try to prove D. If you found an example where they're equal, now just think of any example where they're not equal. What happens when we try negatives? So if we try y equals -1, then x would equal -2. And Max, to your question, I recommend starting with 0. Definitely. 0 tends to be the number that we forget about. If I said to you guys, think of a number, any number, people will often go, 17, 456. They'll think of positive integers, and 0 is one that we forget about, and it's often unique. It behaves in its own way when we're multiplying. It behaves in a unique way when we're taking exponents. Oh yeah, a lot of times when you put things in parentheses, you get very weird emoticons, like parentheses. Is it parentheses 6? Let me try that. Is that the one I'm thinking of? Yeah, it's a devil horn. I don't know, it's random. I like it. So we got funny emojis here on Blackboard. But I like starting with 0. I like starting with 1 because those are often pivot points. So let me give you another example. What would you do with, I'll give you one that doesn't have any upfront information. It's just quantity A, quantity B, and in quantity A we have, let's just keep it simple, y versus y cubed. Pull in your answers for that one. So I think here, this is a good example of why I like starting with the ZONEF of thinking about the 0 and the 1 first. Because if we just look at it kind of with our normal lens. We're like, what's bigger, y or y cubed? A number or when we cube it? Well, when we cube something, it gets bigger, right? But if you automatically start with y is 0, hang on a second, my screen just froze for a second. I don't know why Blackboard does that sometimes. If we start with y is 0, then y cubed would be also 0. And so we kind of don't have to test any more than that, because we'd say to ourselves, okay, in terms of A, B, C, D, clearly if we found a case where they're equal, it's not A or B, but would it always be equal? Is y always equal to y cubed? No. So it has to be D. I don't even need to go through the effort of writing down any new number. If you think of a case where they're equal, and then you can think of a case where they wouldn't be equal, the answer has to be D. So this is what I like to call the equal different method. So you can use ZONEF to test, or you can step back and say, is there a case where they would be the same, and then would they always be the same? What would be another good one to test in this case that wouldn't give us the expected result? Because our expected result, of course, is that B is greater. When we take something cube it, it gets bigger. So what else gives us a non-expected? Aha, negatives. If we take a negative integer, ooh, -1 is interesting. Because -1 cubed is also -1. All right, how about -2? When we cube -2, we get -8, right? So in that case, the greater one, and this is an important point. When we're thinking about these answer choices, oops, going to here, greater here means on a number line. Further to the right is always greater on a number line. So we're not talking about like bigger in absolute value terms. We're not talking about better. Like if I was asking you to compare a student loan debt of $10,000 versus student loan debt of $20,000, well, having less debt would be the better scenario, but 20,000 would be the greater amount, right? So it's interpret this to mean on a number line, what's further to the right. Okay, so I want to push back a little bit, because when someone said negatives, yeah, we got different results here, but what if I had -1/2? What's -1/2 cubed? -1/8, okay. So in this case, yeah, B would be greater because this one is closer to 0, further to the right on the number line. We wouldn't have to test all of these. As soon as you test 2 and you get a different result, you're done. The answer is D. But one important thing to keep in mind with QC, just always across the board, you're never done after testing only one value. Like, you can't just test one thing, get A, and then pick A and move on. You have to ask yourself, okay, I tested something and I got A in this case. Can I think of another case that would give me something different? You're always trying to prove D. Okay, let's try another one. All right, hopefully everyone got a chance to try this one. So one thing that you have to do with QC, you can't just jump right into quantity A and quantity B right away. The first thing that you have to do is unpack or simplify the upfront information. So in this case, n cubed less than n. Here's a general tip. With the GRE, it's really not about math, it's about translation. So you would want to write yourself flashcards where you have, okay, n cubed minus n, or sorry, not minus, n cubed less than n on one side of your flashcard, and then you would want to think, okay, how should I translate that? Put that on the back of the flashcard. So in other words, when do we get a cube that is less than the number itself? All right, negatives. I think we're on to something, but let's get more specific. Fractions. Again, let's get more specific. So here's what I mean by more specific. Think of a number line. And there are basically 3 major pivot points on a number line. There's 0, there's 1, and there's -1. So I like people are being great with the specificity there. It's not just about negatives, because remember, -1, when we cube it, is still -1. It's numbers less than -1 that get smaller when we cube them. Numbers in between 0 and 1, like -1/2 we looked at, wouldn't get smaller when we cube it. It would actually get closer and closer to 0. Fractions between 0 and 1, so positive fractions, like +1/2, would get smaller and smaller and smaller as we cube them. Whereas numbers greater than 1 obviously get bigger when we cube them. So the way to rephrase this is either n is less than -1, or it's between 0 and 1. Between -1 and 0 does not work. 0 itself does not work. So this is kind of a more complicated translation than it looked like. And this is really what the GRE is all about. It's not about doing complicated math. It's about translating the underlying logic of what it is that they're telling us. So with that as our translation, now when we go back to here, n versus n squared. So what's a number that we could test here? Yeah, let's try -2. So what happens when we square -2? We get +4, and so in that case, clearly quantity B is greater. And so looking at A, B, C, D, we should eliminate, if we found an example where B was greater, eliminate A and C. So what should we try next? I saw someone say it earlier, test a fraction. Yeah. So in this case, you know, our mnemonic was ZONEF, but it doesn't mean you have to test those, because would 0 be applicable here? No, we only want to test the things that keep that upfront information true. So not relevant to test 0, not relevant to test 1. And so going through our mental checklist, we try a negative. -2 is applicable. -1/2 wouldn't have been. Now we try a fraction. +1/2, when we square it, gives us 1/4. So in that case, A is greater. That's how we prove D. So if you only test the first thing that comes to mind, if all you thought about was negatives, you might think the answer was B. If all you thought about was fractions, you might think the answer was A. We want to think about all of the possibilities of numbers that can behave differently. So 2 recommendations there. 1, make yourself flashcards. Don't expect that you'll get all of these the first time around, but practice with these. And then maybe write different versions of these kinds of translation and practice translating quickly. When you're thinking about translation, especially with inequalities, think about, well, where is this true on a number line? Barry, I love that question. Let's investigate. New flashcard time. I want all of you to think about how you would translate. I'm going to pick a new variable just to, n cubed is greater than n, greater than m rather. I want everyone to think for a moment about where that would be true, and then we'll discuss. All right, go ahead and tell me in the chat. Aha, for numbers greater than 1, yeah, they get bigger when we cube them. Does it work for -1? What happens when we cube -1? Oh, it'd be the same. Well, we know it's not going to be true for numbers less than -1. It's not going to be true for 0. Is it true for positive fractions? No. Where else on this number line would numbers get greater further to the right on the number line when we cube them? Well, yeah, we already said that. Numbers greater than +1. So that works. So m greater than +1, that definitely fits. I'm just wondering, is there anything else? Aha, between 0 and -1. So we'd say, if we want to say where m is between 0 and 1, we would write it this way. -1 less than m less than 0. We read that as m between -1 and 0. So if we were to cube -1/2, we would get closer and closer to 0. Nice. You know what, let's practice a little bit more of this translation while we're on the topic, because I think that this is something that is not necessarily intuitive, but is something that you'll want to do really quickly on test day. So if the front of our flashcard said, let's go a squared b cubed c, well, let's just start with this, a squared b cubed greater than 0. Take a moment to think about that. Let everyone else think about it for a moment before you tell us in the chat. All right, so if a squared b cubed, if something times something is greater than 0, in other words, we have a product that is positive, what do we know? Well, generally speaking, if we have just a product that's positive, we could either have positive times positive or negative times negative. But in this case, so if it was just a times b, or well, I'll pick new variables, r times t greater than 0, that we would translate as both positive or both negative. Here with exponents it gets a little bit more complicated. So what do we know about a squared? And yeah, Sheila's right on. A squared would always be positive. So if we get a positive overall, b cubed must be positive. And if b cubed must be positive, then b must be positive. And a is positive too? Or aha, Menu is right on. A could be positive or negative. That square is hiding it. A is unknown. A squared we know about, A itself we don't. So you would take all of this and you would say the thing we know, B is positive. Let's go even a little bit more complicated. And it can't be 0. Yes, good point. It could be anything except 0. Very true. How about x times y, let's do this, xy cubed divided by z squared is negative. Take a moment to think about that because there's a lot to unpack. Don't say anything in the chat just yet. Let other people think about it for a sec. All right, if you think you know how we could unpack this, tell us in the chat. How should we interpret this? We've got this fraction that is less than 0. In other words, a fraction that's negative. Interesting. So I like this idea of starting with two cases of thinking, what if it's this, what if it's this? So the thing that we know, switch to a different color to make it easier to see. The thing that we know about z squared is that it has to be positive, right? Our denominator is going to be positive. So if we ended up with a negative overall in this fraction, that must mean that the numerator is negative, right? So if x times y cubed, so two things with odd exponents, remember it's implied here that it's x to the 1, if we get a negative overall, if x times y cubed is negative, then that tells us that x and y, the negative product of two things with odd exponents, x and y have opposite signs. So as Barry put it, they can't both be negative. So they have opposite signs. One of them is positive and one of them is negative. What about z? What do we know about z? Oh, and you had said it before. It can be anything except 0, either positive or negative. We don't know. But I really like the specificity, specifying that it can't be 0. That's important. But really, this complicated thing over here is a way of disguising that we know something about x and y, but we basically don't know anything about z. Practice this kind of translation. Practice making flashcards. I would say for you guys, go home. You know, you're probably already home, but make 4 more versions like this. I mean, I just made this one up on the spot and we translated it together. So make up some of your own and practice translating them so that you're really fast on test day with these. Yeah, and so what you don't want to do on test day is be like, okay, what if it's this and what if it's this, and spend a lot of time unpacking that. You want this to be kind of translation that you have right at the tip of your tongue. All right, let's try something a little bit different, not quite translation, but still in this idea of thinking about good QC process. So take a minute on this one. And please just pull in your answer. Don't do anything in the chat window. take 15 more seconds and then pull in a guess, even if you don't know the answer. Yeah. So let's talk a little bit about terminology here because that is really crucially important on the GRE. So ignoring this for a second, let's do some quick definitions. What is the definition of a prime? Divisible only by itself and 1. And then when we're looking at, when we say the word factor implies positive integer factor. When we see the word distinct, what that really means is don't double count. And I think that was all the terminology that we needed here. There is actually something, I think that this could be its own flashcard here. Prime number greater than 2 is something distinctive. Why specify greater than 2? What's that code for? Not 1, but remember 1 is not prime because 1 wouldn't have factors of itself and 1. So this is actually important. Primes, by definition, divisible by itself and 1, so 2 distinct factors. 1 only has 1 distinct factor, so it's not a prime. And yeah, 2 is the only even prime, so any other prime, any prime greater than 2 will be odd. So they'll sometimes specify that, and that's a way to flag to ourselves, K has to be odd. Maybe that's significant, maybe it's not. Sometimes the GRE will throw things that aren't significant up there, but we know it's prime, we know it's odd. So then, when we're looking at these quantities, let's test values. Is ZONEF relevant here? When we think about ZONEF, well, for K, it's prime, so 0 doesn't fit, 1 doesn't fit. Primes greater than 2, I mean, prime already implies positive integer, but greater than 2 is definitely not going to be negative. Fractions aren't relevant. So this might come down to extremes. Maybe super big ones will behave differently somehow. Not sure. But our usual suspects don't apply here. So what should we test? Give me something to test for K. K equals 3. That's the one that comes most obviously to mind. It's a prime greater than 2. So if that's the case, then 7K would equal 21. What are all the distinct factors of 21? 1, 3, 7, and 21. So we could write it this way. I actually prefer to match them up like this. 1 times 21, 3 times 7, so that we know that they're in those pairs, the factor pairs that will multiply up to that number. But in any case, we've got 4 distinct factors. All right, so when K equals 3, then 11K is 33. So our distinct factors, we've got 1 times 33, 3 times 11. So how many distinct factors? 4. So we got the same numbers here. So in terms of A, B, oops, didn't mean to write those on the same line. A, B, C, and D, what would we eliminate? The answer can't be A, and it can't be B. we found an example where they're both the same. So either they're always the same or there's a case in which they're not the same. We cannot eliminate A, B, and D. If you test one thing, one case, it will only allow you to eliminate 2 answer choices. D is always still on the table if you've just tested one thing. So we could just test now K equals 5. We could go to the next thing. But here's my challenge to you. I want you to think, instead of just testing the next thing, when would these not be equal? In other words, is there a way to get more than 4 factors for one of these or fewer than 4 factors for one of these? And Valeria is onto something. What happens when we try 7? And why is 7 going to behave differently than 3? I mean, there's nothing magical about the number 7 isn't inherently different from 3. They're both primes, but it's because this was the number given to us here, or testing 11 was the number given to us here, those might behave differently. So when we try K equals 7, our factor pairs are 1 times 49 and 7 times 7, but the rule with distinct is that if it's repeated, we don't want to double count it, so we would only get, in that case, 3 distinct factors, not 4. But with 11 times 7, we'd still get 4 distinct factors. So the answer was actually D. But this one, so I wrote this question modeled on a couple of real questions, one from the official guide and one that I saw in the real GRE, but this one is like a little bit harder even for some reason, and I think it's because, yeah, we test 2 things and we're like, same, they behave the same, that's easy, it's the same. So here's my, what I would say in general on that. Beware of what I call, beware the easy C. If they look identical, it's probably too easy for it to be C, right? Like, they wouldn't want someone at a glance without doing any thinking to be like, structurally, this is the same as this, right? So must be the same, must be C. That's what, that's what a 5th grader would pick without doing the work, right? You want to be more skeptical than that. And really, that's my best advice on the verbal side of the GRE as well as the quant. Be skeptical. Distrust the test writer. Don't distrust them like they can't lie to you, but they are very tricky. Assume that the test writer is being sneaky and that nothing is as easy as it seems. If it looks too easy, it probably is. Something else is going on here. Cool. One more cool thing I want to show you on QC. Give this one a try and then we'll discuss. Take 20 more seconds. Okay, so remember earlier when I said that QC is a great opportunity to save some time, and I'm going to show you why. There is a long way to do this problem that maybe isn't that efficient and maybe not that exact, and then there's a shorter way to do the problem. So if if we tested numbers here, I mean, testing numbers is sometimes a good approach, but let's see. N less than 3. Okay, so I'm going to try 2. If n is 2, 5 times n is 10, minus 4 is 6, 2 times 2 is 4, plus 3 is 7. Okay, so clearly this one's greater, so we can get rid of this one, we can get rid of this one, and then, I like that idea. Try something different. If we tried a positive, let's try a negative. So 5 times negative 1, negative 5 minus 4 gives us negative 9. Negative 1 times 2, so negative 2 plus 3 is positive 1. So not only is that still greater, but we're getting farther and farther apart. So it seems like if we tested 2, it seems consistent. We should choose B. Is 50 relevant? I like this idea of trying an extreme, but are we allowed to try 50? We have to keep our upfront information true. We're only allowed to test things within those given constraints. I like the idea of negative 50. Try something way on the other side. All right, so negative 50 times 5, negative 250 minus 4, negative 254, versus 2 times negative 50, so we've got negative 100 plus 3, negative 97. Again, we're getting further and further and further apart. So the further negative we go, further down the number line, we're still getting the same result. But there is something we tried a positive and a negative, we tried an extreme. Ooh, Sheila. I bet a lot of people are like, where the heck did you come up with that number? But the one thing that we haven't tried is fractions. It was less than 3, but we jumped right to 2. Maybe there's something between 2 and 3. There is a better way to solve this problem. And what Sheila was doing, which is brilliant here, don't test numbers. If you can, so imagine this. It's going to turn out, well, maybe here's a better way to imagine this. Let's say that I have in quantity A, I've got the number 2, and in quantity B, I've got the number 4. Clearly, it's the case that this one is greater, right? But imagine that I add 3 to both sides. If I have an inequality and I do the same thing to both sides, I've maintained the same relationship, right? Quantity B is still greater. I could subtract the same thing from both sides, and I would maintain the same relationship, where quantity B is still greater. I could multiply both sides by the same thing, and I'd still maintain the same relationship, because the rule is what you do to one side, you do to the other. The only thing that we'd have to watch out for with inequalities is what? The danger in inequalities is, yeah, if we multiply by 0 or negatives, or try to divide by negatives, exactly. But you can, with a standard, if this wasn't QC, if this was just a standard inequality, we know that what we do to one side, we can do to the other. We can add the same thing to both sides, subtract the same thing, multiply or divide positives both sides, and we maintain the same relationship. The bigger side stays bigger. So we can apply that thought process here, even though we don't know which way the inequality goes. Maybe it'll turn out that this side is greater. Maybe it'll turn out that this side is greater. Maybe they'll turn out to be equal. But imagine that there's an inequality sign, or maybe an equal sign that's in the middle that we just can't see. This is what we call the hidden inequality strategy. Pretend there's an inequality there that you just can't see, And what you do to one side, you're allowed to do to the other. So if we wanted to simplify, we could add 4 to both sides. And then it becomes 0 over here, we disappear. And now what we're comparing is 5n, comparing it to 2n plus 7. And then we could simplify further by subtracting 2n from both sides. And then this cancels over here. When we simplify, what we're comparing is what's greater, 3n or 7. So simplify further. We're going to basically extend this, pretend this hidden inequality goes all the way down. We're allowed to divide by a positive, divide both sides by 3, and then our comparison is n to 7/3. What's the approximate value of 7/3? Yeah, 2 1/3. So 2.3333 repeating, so a little greater than 2. So if our question is which one's greater, n or 2.333? Well, our constraint is that n is less than 3. But does that mean that n is greater or less? N, what if, now we could test values. What if n equals 2.5? Then n would be greater than quantity B. N would be greater than 2.3. But if n was 0, it would be less than, so we don't know. So here the answer would be D. But if we were given different upfront information, imagine that our original constraint, instead of n less than 3, what if our original was n less than 1? In that case, if we're given that n is less than 1, and once we simplify, we're comparing n to 2 1/3, then clearly 2 1/3 would have to be greater. So in that case, the answer would be D, or B rather, yes, B. So it matters what that original constraint is. But this idea of the hidden inequality, we can simplify, maintaining the same relationship as before, we can then compare. So anytime you see algebraic expressions in quantity A and quantity B that have the same variable and look like they could be simplified, try this hidden inequality thing. So here's a difficult question. When people say, how do I decide quickly on test day? I don't have a great answer to that because, like for me, I have muscle memory. I look at a problem and I immediately know instinctively which method to use. But the reason that I have that instinct is every problem I've seen, I've done it both ways, so that I know for myself when it works and when it doesn't, when I like to use one or the other. So the unsatisfying answer is you won't know right away. You have to practice it both ways. So as you're doing practice problems, see if you could do them different ways. But the signal for when it's going to work is if you have the same variable in each quantity A and quantity B, and there are things like -4, +3, things that you could move from one side to the other easily. If they were doing it exactly correctly, each answer would have about a 25% chance of being right. The problem is the official guide is so thin, has so few problems in it that we could run, we've run an analysis of that. I think in the official guide, D ends up being right 29% of the time instead of 25% of the time, but we don't know if that's representative of the real test. So this is just a taste, a little flavor of some of the strategies that you want to master to do well on the GRE. If you're interested in doing more, Manhattan Prep has lots of great materials, we've got books, we've got workshops, we've got classes. You're always welcome to sit in on a trial class for session 1. We'd love to have you. But, you know, you definitely don't need to spend a fortune to do well in this test. You do need to put in the work. It takes practice. As we've seen, it's learning a foreign language, so give yourself time to practice that. So I wish you the very best of luck. It was great having you, and hope to see you at the next free prep hour. Take care.